This presentation treats the Hilbert Book Model project. The target of the project is the generation of a mathematical model that can be used in order to investigate the structure of the foundation and the lower levels of the structure of physical reality. I am a retired physicist. I spent my career in high-tech industry.
This lecture introduces you to the Hilbert Book Model. The model deviates considerably from the models that constitute contemporary physics. The model is strictly based on a trustworthy foundation. The Hilbert Book Model selects Hilbert spaces for that purpose. The model applies a system of Hilbert spaces. These Hilbert spaces all apply the same underlying vector space. The Hilbert Book Model represents my personal view on the lower layers of fundamental physics. A quaternionic Hilbert space can easily be structured as a dynamic model in which all past, present, and future geometric data are stored. Therefore, the corresponding space progression model becomes paginated like a book. It consists of an ordered sequence of static submodels. That is why the project got its name Hilbert Book Model. Please look at the book or paper, The Setbacks of Theoretical Physics. This is part 6 of a multi-part presentation. This part concerns potentials, gravity, shock fronts, refraction, electronic imaging, holographic systems, holographic universe, multiverses, partitions of outer space, vertebrates, the visual trajectory of vertebrates, how the brain works. In physics, potential energy is the energy held by an object because of its position relative to other objects. The potential at a location is equal to the work, energy transferred, per unit of actuator influence that would be needed to move an object to that location from a reference location where the value of the potential equals 0. We consider the potential to be 0 at infinity. Thus, if infinity is selected as the reference location, then the potential at a considered location is equal to the work, energy transferred, per unit of actuator influence that would be needed to move an object from infinity to that location. The potential at a location represents the reverse action of the combined actuator influences that act at that location. The influence of similar actuators can superpose. Thus, a geometrical center of these influences defines the location of the virtual location of a representant of the considered group of actuators. This virtual representant has the potential of a point-like actuator of the same influence type. In the Hilbert Book Model, static actual point-like actuators other than charges do not exist because the embedding field tends to remove them as quickly as possible. However, static virtual point-like actuators can be defined. The first order change contains 5 terms, 2 scalar terms, and 3 spatial terms. In each of these subgroups, the terms can compensate for each other. In the group of spatial terms, the gradient of the scalar part of the quaternionic field can compensate for the time variation of the spatial part of the quaternionic field. If the curl of the part of the quaternionic field can be neglected, then the gradient of a local potential can cause a time variation of a spatial field that describes the movement of influenced objects. If these are massive objects, then these objects will be accelerated. So, the spatial field will represent a force field. The actuators of spherical responses discussed in this paper are listed in the table. This is the second part of the table. Electric fields and gravitational fields differ fundamentally in their start and boundary conditions. Electric charges can attract or repel each other. Masses will always attract each other. Hop landings are matter actuators. Dark matter objects are the result of matter actuators. The footprint of a fermion is a collection of matter actuators. This collection represents an ongoing hopping path. The ongoing hopping path features a recurrence cycle that depends on the type of the fermion. The recurrence cycle determines the mass of the fermion type. Forces require a point of engagement. Fields do not own a point of engagement. For quaternionic functions, the first-order change already connects the gradient of a scalar field to the time variation of the corresponding spatial part of the field. It suffices that the universe field shows a gradient in its scalar part and that the spatial part of the field moves uniformly. Thus, a gravitational potential raises an acceleration of the moving spatial field. Intuition cannot tell you this, but mathematics does. Gravitation is a potential of the universe field. Gravitation is not a potential of the electric field. This confuses many physicists. The inspected location is the location of a hypothetical test object that owns an amount of mass. It can represent an elementary particle or a conglomerate of such particles. This location is the target location in the embedding field. The embedding field is supposed to be deformed by the embedded objects. Observers can access information that is retrieved from storage locations that for them have a historic timestamp. That information is transferred to them via the dynamic universe field. This dynamic field embeds both the observer and the observed event. The dynamic geometric data of point-like objects are archived in Euclidean format as a combination of a timestamp and a three-dimensional spatial location. The embedding field affects the format of the transferred information. The observers perceive in space-time format. The Lorentz transform is a purely mathematical transformation. The hyperbolic Lorentz transform converts the Euclidean coordinates of the background parameter space into the space-time coordinates that are perceived by the observer. The embedding field may be deformed. This also affects the transferred information. Photons follow geodesics in the embedding field. In dynamic fields, shock fronts move with speed c. In the quaternionic setting, this speed is unity. In flat dynamic fields, swarms of triggers of spherical pulse responses move with lower speed v. For the geometric centers of these swarms still holds. If the locations x, y, z, and x accent y accent z accent, move with uniform relative speed v, then a hyperbolic transformation that relates two coordinate systems is known as a Lorentz boost. The Lorentz boost can be derived in many ways. Wikipedia lists several of these methods. The author prefers the derivation based on group properties. This transformation can concern two platforms P and P accent on which swarms reside and that move with uniform relative speed v. However, it can also concern the storage location P that contains a timestamp tau and spatial location x, y, z. And platform P accent that has coordinate time t accent and location x accent, y accent, z accent. Einstein exploited this possibility to give the platforms a physical interpretation and called them inertial platforms. Inertial platforms are not deformed by gravitational actuators. In this way, the hyperbolic transform relates two platforms that move with uniform relative speed. One of them may be a floating Hilbert space on which the observer resides. Or it may be a cluster of such platforms that cling together and move as one unit. The other may be the background platform on which the embedding process produces the image of the footprint. The Lorentz transform converts a Euclidean coordinate system consisting of a location x, y, z, and proper timestamps tau, into the perceived coordinate system that consists of the space-time coordinates, x accent, y accent, z accent, ct accent, in which t accent plays the role of coordinate time. The Lorentz transform converts a Euclidean coordinate system consisting of a location x, y, z, and proper timestamps tau, into the perceived coordinate system that consists of the space-time coordinates, x accent, y accent, z accent, ct accent, in which t accent plays the role of coordinate time. Space-time is ruled by the Minkowski metric. In flat field conditions, proper time tau is defined by, and in deformed fields, still. Here ds is the space-time interval and d tau is the proper time interval. dt is the coordinate time interval. The deformation potential energy U of r at the event horizon r equals r event horizon of a black hole is supposed to be equal to the mass energy equivalent of an object that has unit mass m equals 1 and is brought by an agent from infinity to that event horizon. Dark energy objects are energy packages in the form of one-dimensional shock fronts that are a candidate for this role. The deformation potential energy U of r at the event horizon r equals r event horizon of a black hole is supposed to be equal to the mass energy equivalent of an object that has unit mass m equals 1 and is brought by an agent from infinity to that event horizon. Dark energy objects are energy packages in the form of one-dimensional shock fronts that are a candidate for this role. At the event horizon, all energy of the dark energy object is consumed to compensate for the deformation potential energy at that location. No field excitation and in particular no shock front can pass the event horizon. In the equation, the mass m of the test object could have been replaced by the mass msh of the spherical shock front that represents the dark matter object or by the mass me of an electron. In the case of M, the equivalent energy is the energy of a dark energy object that is represented by a one-dimensional shock front. In the case of MPH, the equivalent energy is the energy of the annihilation or creation photon of the electron. The annihilation and creation photons have the same duration and contain the same number of shock fronts. That number is the same as the number of spherical shock fronts in the footprint of the electron. This is the reason of the mass-energy equivalence. The event horizon appears to block all field excitations. This means that the image of the floating separable Hilbert space that represents the electron cannot pass the event horizon. It is postulated that this holds for all floating Hilbert spaces in the system. Time dilatation is defined by a tick delta t of a coordinate time clock is smaller than the tick delta tau of a proper time clock. In a gravitation potential, the relation is. Here VE is the escape speed. Length contraction is defined by. In a gravitation potential, the relation is. Here L0 is the length in free space. The Lorentz transform also gives the transform of the rest mass to the mass that is relevant when the embedding field moves relative to the floating platform of the observed object with uniform speed spatial v. In that case, the inertial mass m relates to the test mass m0 as this indicates that the formula for the deformation potential at distance r must be changed to the relation between inertia and mass is complicated. We apply an artificial field that resists its change. The condition that for each type of massive object, the deformation potential is a static function, and the condition that in free space, the massive object moves uniformly, establish that inertia rules the dynamics of the situation. These conditions define an artificial quaternionic field that resists change. The scalar part of the artificial field is represented by the deformation potential, and the uniform speed of the massive object represents the spatial part of the field. The first-order change of the quaternionic field can be divided into 5 separate partial changes. Some of these parts can compensate for each other. Mathematically, the statement that in the first approximation nothing in the field psi changes indicates that locally, the first-order partial differential grad psi will be equal to 0. Thus, and these formulas can be interpreted independently. For example, according to the equation, the variation in time of psi r can compensate the divergence of spatial psi. The terms that are still eligible for change must together be equal to 0. For our purpose, the curl of the spatial field psi is expected to be 0. The resulting terms of the equation are in the following text plays psi the role of the spatial field and psi r plays the role of the scalar deformation potential of the considered object. For elementary modules, This special field concerns the effect of the hop landing location swarm that resides on the floating platform on its image in the embedding field. The special field reflects the activity of the stochastic process and the uniform movement of the geometric center of the floating platform over the embedding field in the background platform. It is characterized by a mass value and by the uniform velocity of the floating platform concerning the background platform. The real, scalar, part conforms to the deformation that the stochastic process causes. The spatial part conforms to the speed of movement of the floating platform. The main characteristic of this field is that it tries to keep its overall change at zero. The author calls psi the conservation field. At a large distance r, we approximate this potential by using the formula. Here m is the inertial mass of the object that causes the deformation. The new artificial field considers a uniformly moving mass as a normal situation. It is a combination of scalar potential and spatial speed v. This speed of movement is the relative speed between the floating platform and the background platform. At rest, this speed is uniform. If this object accelerates, then the new field tries to counteract the change of the spatial field, by compensating this with an equivalent change of the scalar part of the new field. According to the considered spatial part of the first-order partial differential, this equivalent change is the gradient of the real part of the field. This is equal to the acceleration a. This generated spatial field acts on masses that appear in its realm. Thus, if two uniformly moving masses m and m exist in each other's neighborhood, then any disturbance of the situation will cause the deformation force. Here is the inertial mass of the object that causes the deformation. m0 is the rest mass of the observer. The inertial mass m relates to its rest mass m0 as. This formula holds for all elementary particles except for quarks. The problem with quarks is that these particles do not provide an isotropic symmetry difference. They must first combine into hadrons to be able to generate an isotropic symmetry difference. This phenomenon is known as color confinement. In the formula that relates mass to force, the factor gamma that corrects for the relative speed can be attached to m0 or to m0. The force relates to the temporal change of the spatial momentum vector p of the observer. The spatial momentum vector p is part of a quaternionic momentum p. The momentum depends on the relative speed of the moving object that causes the deformation which defines the mass. The speed is determined relative to the field that embeds the object and that gets deformed by the investigated object. For free elementary particles, the speed equals the floating speed of the platform on which the particle resides. Relevant formulas are if then and. Here Einstein's famous mass-energy equivalence is involved. if then and. Here Einstein's famous mass-energy equivalence is involved. The disturbance by the ongoing expansion of the embedding field suffices to put the deformation force into action. The description also holds when the field psi describes a conglomerate of platforms and m represents the mass of the conglomerate. The artificial field psi represents the habits of the underlying model that ensures the constancy of the deformation potential and the uniform floating of the considered massive objects in free space. Inertia ensures that the third-order differential, the third-order change, of the deformed field is minimized. It does that by varying the speed of the platforms on which the massive objects reside. Inertia bases mainly on the definition of mass that applies to the region outside the sphere where the deformation potential behaves like the Green's function of the field. Next, the definition of the conservation field supposes that the swarm which causes the deformation moves as one unit. Further, the fact is used that the solutions of the homogeneous second-order partial differential equation can superpose in new solutions of that same equation. The popular sketch in which the deformation of our living space is presented by smooth dips, is obviously false. The story that is represented in this paper shows the deformations as local extensions of the field which represents the universe. In both sketches, the deformations elongate the information path, but none of the sketches explain why two masses attract each other. The above explanation founds on the habit of the stochastic process to recurrently regenerate the same time average of the deformation potential, even when that averaged potential moves uniformly. Without the described habit of the stochastic processes, inertia would not exist. The applied artificial field also explains the deformation attraction by black holes. The artificial field that implements mass inertia also plays a role in other fields. Similar tricks can be used to explain the electrical force from the fact that the electrical field is produced by sources and sinks that can be described with the Green's function. Electron optics concerns the imaging of charged particles by artificially constructed electric or magnetic fields, or by existing electromagnetic fields. Construction elements are metallic electrodes that are put at a given voltage or coils that carry electric currents. Radio transmission is a special kind of electron optics. Refraction occurs at the borders of transparent media in which information transfer occurs with constant speed. The information transfer can take place through chains of absorption and re-emission cycles. In free space, nothing exists that absorbs or emits photons, but photons can travel through free space along geodesics. Refraction enables the construction of lenses, fiber plates, optical fibers, prisms, and mirrors. Transparent optical lenses and tiny apertures can act as Fourier transformers. They map distributions of photons in position space into distributions in frequency space. These distributions are called holograms. Holograms can be captured in photographs. Also, metal mirrors imprinted with phase patterns can generate holograms when a coherent beam of light is reflected by the imprinted mirror. Holograms became popular products, and the front page, Scientific American, was once covered with a hologram. The holographic principle is an axiom in string theories and a supposed property of quantum gravity that states that the description of a volume of space can be thought of as encoded on a lower dimensional boundary to the region, such as a light-like boundary like a gravitational horizon. First proposed by Gerard 't Hooft, it was given a precise string theory interpretation by Leonard Susskind, who combined his ideas with previous ones of 't Hooft and Charles Thorne. This and the next slides are copied from Wikipedia. Leonard Susskind said, "The three-dimensional world of ordinary experience, the universe filled with galaxies, stars, planets, houses, boulders, and people, is a hologram, an image of reality coded on a distant two-dimensional surface." As pointed out by Raphael Bousso, Thorne observed in 1978 that string theory admits a lower dimensional description in which gravity emerges from it in what would now be called a holographic way. The prime example of holography is the ADS/CFT correspondence, see Wikipedia. The holographic principle was inspired by black hole thermodynamics, which conjectures that the maximum entropy in any region scales with the radius squared, and not cubed as might be expected. In the case of a black hole, the insight was that the information content of all the objects that have fallen into the hole might be entirely contained in surface fluctuations of the event horizon. The holographic principle resolves the black hole information paradox within the framework of string theory. However, there exist classical solutions to the Einstein equations that allow values of the entropy larger than those allowed by an area law, radius squared, hence in principle larger than those of a black hole. These are the so-called Wheeler's bags of gold. The existence of such solutions conflicts with the holographic interpretation, and their effects in a quantum theory of gravity including the holographic principle are not yet fully understood. The Hilbert Book Model bets on a mixture of space compartments and balance equations. The human brain and visual tract shows remarkable structure and behavior. The humans share this with all vertebrates. Vertebrates evolved in a very dim environment, where living species relied on optimal perception in low light level conditions. optimal detection of low-dose radiation of visible quanta was required both for nurture and for timely fleeing for predators. These conditions prepared the evolution of the human species. It determined the structure of the vertebrate visual tract and the handling of noisy low-dose quanta that carry the required information. This does not mean that non-vertebrates cannot become intelligent. Inkfish are well-known exceptions. Image-intensifying devices are designed to cope with the low-dose conditions that vertebrates had to cope with during the early stage of their evolution. In the 70s of the 20th century, the perception of low-dose images was visually determined by means of line pair charts or Land-Old-C charts. These were inaccurate and very subjective tests that strongly depended on the condition of the investigated person. My task was to introduce more objective measuring methods. Several institutes were already performing direct current and root mean square measurements on the results of stochastic processes. These instruments showed very unstable results, which had to be damped over long integration periods. Some high-tech optical institutes were experimenting with measuring the optical transfer function, OTF, of optical and electron-optical equipment. Our laboratory applied the old Delft transfer analyzer, ODTA, for that purpose. The OTF measures sharpness in an objective way. To measure the capture of quanta objectively, an instrument was designed to measure the detective quantum efficiency, DQE, of image-intensifying devices. These measuring methods were accepted as STANAG standards and later as IEC, ISO, and DIN standards. These standards aim at optical lenses, night vision devices and on X-ray image intensifier devices. The approach was based on the results of two scientists that became famous in the 60s and 70s and got the Nobel Prize for their work, David Hubel and Torsten Wiesel. They published in books and in Scientific American. You can still read these articles in the digital version of Essay. Please, search Google for David Hubel and Torsten Wiesel. David Hubel and Torsten Wiesel discovered that in the visual trajectory of the vertebrates, the information is encoded by a sequence of processors that apply a mask to filter the information. If the signal-to-noise ratio of the past information is too low, the sequence is stopped, and the visual tract is no longer bothered by the signal. It appears that not only the visual tract up to the fourth level of the brain of the vertebrates works this way, also the rest of the vertebrate brain stops treating information for which the signal-to-noise ratio is too low. This prevents the individuum from getting chaotic. The signal-to-noise level at which the investigating stops differs per individual, is influenced by emotions, and can be influenced by drugs. If, like the author, the individual has a low signal-to-noise barrier, he may be able to associate noise with earlier gained knowledge. In this way, that individual can experience eureka events and classify them as discoveries. This is how the author discovered the special set. The Hilbert Book Model embraces the special set. This special set determines in detail how the separable and non-separable Hilbert spaces behave. For physical reality, one of the members of a system of Hilbert spaces plays the role of background Hilbert space. This happens both for systems of separable and for systems of non-separable Hilbert spaces. This special role confuses many scientists. The system of non-separable Hilbert spaces invites the compartization of space. This idea stimulates the ideas of a holographic universe and parallel multiverses. This ends part 6 of a multi-part presentation. This part concerns potentials, gravity, shock fronts, refraction, electronic imaging, holographic systems. Holographic universe, multiverses, partitions of outer space, vertebrates, the visual trajectory of vertebrates, how the brain works. Part 7 concerns modules, modular systems, modular system communities, modular system types, modular system hierarchies. Modular versus monolithic system generation, resilience of modular system communities. Interfaces, specification of interfaces, archival of interfaces, living species, RNA and DNA, intelligence, robots, the next evolution step.